Hey everyone, good afternoon. Thanks for making your way down the hall to the Machine Learning Lab track. We're super excited about our speaker, Yannis Daras, this afternoon. Yannis started here at part of his journey, at least at UT Austin. He went from Texas for his postdoc. He's at MIT now. And he's a postdoctoral scholar there. He's going to be showing some of this research, and he will soon be starting as a professor at MIT, which is some new news, and we're super happy for him. And so please welcome in, giving us a welcome back to UT to Yannis.
Okay, hello everyone. Super excited to be back at UT. And today we're going to talk about generative models. Everyone is excited about generative AI, but in this talk there's going to be a twist. And the twist is that we are going to be training these generative AI models from bad data. And hopefully, by the end of this talk, you'll have a sense about why this problem is important and what are some interesting questions and future work around this problem. I want to say that this is not like a single paper. It's more like a series of works that started at UT Austin a few years back and then expanded to other universities and a lot of great collaborators. And I'm super thankful for all of them that have helped me with this agenda. Okay, so the talk is going to be about bad data, but maybe we can spend 1 minute talking about good data. And what is a good data point, for example? And I want to argue that there is not a strict definition, but maybe one thing that we can say is that good data points are some data points that give us a lot of information about the world. Let's look at this image, for example. Okay, then you look at it, and the first thing that you realize that it's probably like a painting in some village in the medieval times and so on. So you get some sense. But then the more you look at the image, the more things that you realize. You see that there is some knight sleeping in the corner of the image. Then you see that there are some cards falling from the window. You see that there are some patterns in the roof. And then you see that there is some fire, and everyone in the village is kind of stressed about it, and they want to put it out. So all of this information is coming from a single data point. From just looking at a particular image, you can tell that there are villages where people do a lot of things and that people are sleeping and cards are falling down. And all of this information is coming from a single image, okay? But then if you were to see a corrupted version of this image, and there are many corruptions, but let's look at the simplest corruption, which is a downscaled version of this image. Maybe you still have some information about the world. Maybe you can still tell it's a painting. And maybe you can still tell, it's some village. But then a lot of this fine-grained information is now lost. The night is now lost. The cards falling from the window are lost. The patterns in the roof as well. Even the fire is kind of erased. So all of this information that was present in this previous data point, it is now kind of lost. So in some sense, we wouldn't like the sample as much as we'd like the previous one because it gives us less information about the world. Okay. And if you take this idea to the extreme and you look at some other corruptions where, let's say you have an initial image and 99% of the pixels of this particular image are erased. In that particular setting, you would say that this particular image is very useless because I have no idea how to use it or what information I can get about the world. And you have this pessimistic view of things, and you say, bad data, they're not really useful when I train generative models. And this is partially true when you look at them in isolation, but it turns out that a lot of bad data actually accounts for something, which means that you can actually collect these data sets where all of the samples are corrupted, and maybe the corruption is really high. For each particular image in the data set, 99% of the pixels are missing. Yet, you can have a corruption-aware training that is compatible with the way we train models, like diffusion models or LLMs, and then you can have a model that can spit out at inference time images that have no corruption at all. And this model is trained without ever seeing any clean image. And I want to say at this point, this is not the most impressive faces that you have ever seen. That is correct. If you go to ChatGPT or Gemini and you ask it to generate a human face, you will probably get better outputs. But the very fact that you can do it just by having a very, very corrupted data set and nothing else, it's kind of interesting. And we'll see that it's going to be actually useful going on. And there is nothing particular about this set of corruption that we saw before, the missing pixels, because you can do it for other corruptions as well. Here's another example where the images are corrupted, but they're corrupted in a different way. We have added additive Gaussian noise to the pixels, and then yet again, you can have a model that is doing a reasonable job in producing human faces without ever seeing an uncorrupted image. You can go and do this in the latent space, so where you have a lot of images, maybe with captions, and now you have a latent space, and you corrupt in this latent space. And then yet again, you can have a model that you can prompt it and say, oh, I want a graffiti of a robot. And it can do it, okay? It can do it pretty reasonably well. Now, in all of these setups, the corruption was kind of like simple. But in real data sets, this is not what's happening, okay? What is happening a lot of the times that maybe we have a set of images that we really, really like. This is actually the distribution that we're going to be sampling from. Maybe, let's say, if we care about the image domain, these are images that are coming from professional photographers, and they went out with their professional cameras, and they took these great pictures. But then, not all images in the web or in your data set are like this, okay? Because maybe my little brother went around with his phone and took a bunch of pictures, and now these pictures are not that great, and they leak in these real data sets. When you form these like gigantic data sets from the web and from other sources, you will have a lot of images that are corrupted in some sense, not like before where like pixels were missing at random, but they're still corrupted in some sense. And maybe there are synthetic images as well, or maybe they're out of distribution images. And if you just naively train your model on this, you will see that at inference time, the outputs are not that great. And this is fine, because the model believed during training, if we have no mitigation, that like these were actually samples from the distribution that we care about. It turns out that the simple generalizations of the ideas that we had before from the masking case and the additive Gaussian noise case, they can actually like learn from these bad samples without affecting the quality. And that is actually like what we are hoping. We hope to leverage these bad samples because they still have information about the world. Like, we still capture the real world a lot of the times, but not all of the samples have the same quality. And we want to be accounting for that when we train. We want to be doing this corruption-aware training. And you can extend this idea to other domains like proteins. We'll talk about this in a bit. Or you can do this even for text. You can have these data sets where like every point does not even look like English. It says the continued weird narrator value and so on. It doesn't even parse, but yet you can train a model. And if you are aware of the fact that something bad happened to your data, you can actually get a model that can produce like reasonable text at inference time. And again, it's not a ChatGPT model, but it's interesting that it can do it. Okay, so this was like kind of the marketing pitch of the talk. Now I want to give you a glimpse of the techniques. And of course, given the short duration of this talk, we're not going to be able to go very, very deep. So I'm going to do something like kind of annoying, which is that I'm going to talk about the simplest corruption, which is going to be this additive Gaussian noise case. And when I talk about this, you might feel like, oh, why are we doing this? Like as we said, real data sets, they have these diverse corruptions that cannot be explicitly modeled and so on. But yet, these techniques that we are going to be developing for this additive Gaussian noise case, they will turn out to be super useful, even if we go to these arbitrary cases. So I want to give you a glimpse of these techniques and to kind of demonstrate that even in this academic setting of where like you have a very simple corruption, there is interesting things to happen. And then these techniques that we are going to be developing, they can extend, and I will show you how to extend them. Okay, we are going to be instantiating this framework for diffusion models. Basically, there are two paradigms right now for generative modeling. There is like the autoregressive models that are very, very dominant in the text domain, and then for images and other continuous distributions, there's the diffusion models. And these models are actually like really, really good. Okay, you can like they can generate these images that are super like realistic and super creative, and like 2 or 3 years ago, they couldn't do this. And it's actually pretty surprising that they can do it. And they can do other things as well. You can give them an image, and you can ask them to modify it. You can make it like Picasso style, or you can make it Texas style. And like these models can actually, do a pretty good job of it. And despite the fact that they do these like pretty interesting and pretty complex things, they are trained in a very, very simple way. So I'm going to talk 1 minute about this training, and I will show you how you modify this training when you don't have clean data, okay? So how are they trained? They trained in a very simple way. You get an image from the data set, and then you start corrupting it by adding noise. And you can corrupt it in different noise levels. So you have all of these versions of your image, where like at a particular time, we call it, this time t, you have some noisy input, okay, that has a particular noise level. Then what you do, this is the only thing that enables this magic, is that you train your model to basically be a denoiser. So it takes as input this noisy input xt, and it's trying to predict this clean image x0. And this is the only thing that you do. You have an L2 loss, where like you have your clean images, you corrupt them, and then you create these pairs of clean and corrupted, and you train your model to be this denoiser. And there is a very strong mathematical foundation around these models that tells you that this particular denoising procedure, if you do this and you have all of these denoisers, then you can actually be sampling from a distribution that you care about, and you can be generating these particular images that are so creative and so nice. And the only thing that you need to do is you need to train all of these denoisers. So this is normal world when you have clean data. But let's go to our setting, okay? In the simplest corruption setting, there is an adversary, there is a bad guy, that comes and says, okay, look, I'm not going to give you these clean images. I'm actually going to give you images at a particular noise level. We call it in nature. This is the noise level of the bad guy. and they tell us this is all you have. And you still want to be training these denoisers because we know that if we had good data, we could train these denoisers, and this framework works. This is a really good framework and can actually work. But what happens if we don't have clean data, okay? We want to train these denoisers, and we don't have this target x0 there. Like, this is a big problem, because before we're supervising the model to go from this xt, the noisy image, to the clean image x0. But in this particular setting, we don't have it, and yet we still want to do the same thing. We want to train denoisers for all times, which includes noise levels above the noise level of the dataset, and also noise levels below the noise level of the dataset. And these two problems, they're both hard, very hard. Even if the corruption case is very, very simple, like here, which is like additive Gaussian noise, still like doing this is a pretty hard problem, because in one setting, you want to train denoisers without having the clean targets. And on the other side setting, you don't have the targets, but you also don't have the inputs. So you want to train a denoiser that denoises without having either the inputs or the targets. So I'm going to talk about this easier problem. And here's what we do there, okay? This technique that we're going to develop here in this simple setting, it's actually going to be useful. So here's how it works. You say, look, I would like to have this extra noisy input T, and to go to the clean image x0. This is the denoiser that we would like to train. But unfortunately, we cannot train this denoiser. Why? Because we do not have this clean image x0 to supervise it to. And yet we say, OK, how about we try to train what I call the lazy denoiser. So this lazy denoiser, this g theta, is doing the following thing. It's only removing the noise that we added. So the bad guy, again, they gave us this images at this particular noise level T nature. And then we added extra noise. We bring it to this noise level T. And then we train this very lazy denoiser that only removes not all the noise, but just the noise that we added. So it goes from T to T nature. This is not what we want, but this is something that we can train. Again, we can like create this like training procedure where we have these pairs. This xt nature is what the bad guy gave us, and then we add extra noise. We create these xt's, and then we train the model to go from xt to xt nature, which is a lazy thing, but yet we can do it. Now here is the interesting part. Turns out this very nice lemma works. And here's what this lemma is telling you. It's telling you that the thing on the left is the target denoiser that you would like to train. This is the denoiser that is not lazy. It's actually removing all the noise, going from like T all the way to 0. But we cannot really train this denoiser because we do not have access to the clean images. Yet, this lemma says that if you have the lazy denoiser that only removes the noise that you added, after you train it, you have the optimal solution, you can massage it and convert it back to the denoiser that you want. Intuitively, this basically is saying that like, if you want to remove some noise, all it matters is to find the direction of the noise vector. And if you know how the direction of the noise vector goes, you can remove more noise by scaling it up appropriately. And this turns out to be really, really good result and helpful result for us, because we can just like leverage it and write down a loss function that only involves noisy inputs and no clean data at all. And without any clean data, we are guaranteed that we are going to have the same minimizer. So if we are able to solve this optimization problem to really like, run gradient descent with a very big model for a lot of time, and we have a lot of data, we are going to be able to find this good denoiser without ever having like good targets. And this is a way to like learn denoise without clean data. The other problem is even harder, but I'm not going to talk about it. But just to give you a sense that, even in this simple corruption case where like everything is like known, how you have additive Gaussian noise and you know the noise level, it's still like an interesting problem to be solving. Okay. Okay, so that is okay. We might solve like at least partially this additive Gaussian noise problem. But if you were to go to the real data, the data sets are not like this. They have some corruption, as we discussed. But this is not the additive Gaussian noise corruption. But even like the most familiar data sets that we know, like ImageNet, they do have some corruption. And we know that there is something wrong, because what you can do is you can like, take the images and like score them according to some quality metric, or maybe ask humans to rank them. And you will see that there are some images on the left where like all the humans and all the models that like score for quality agree that they're amazing. And there are like some other images that they're not that great. We don't really know what happened to them. We cannot say, okay, this is additive Gaussian noise of that particular noise level, but we know that they're not that great. And the question is like, can we kind of reuse these techniques that were very, very like tailored to the additive Gaussian noise case to this like more arbitrary case and this harder corruption? And to do this, maybe let's play a game together to figure out the technique. here's the game. There's going to be a clean image and a blurry image. And now I think we can all agree which one is which. So we can say the left one is the clean, and the right one is the blurry. But here's what happens now. I added noise to both of these images, the same amount of noise. And I want you to kind of guess which one is which. So raise your hand if you think that the image on the left is the clean image plus noise. So if you believe that the image on the left is the clean image plus noise, raise your hand. OK, and if you believe, who believes that the image on the right is the clean image plus noise? OK, much more hands. But you're wrong. You're wrong. Okay? Even in this very easy, I was hoping that you would be wrong later. So the game had like more stages. But the idea is that like you were wrong very, very early on. The idea is that even the two distributions are very, very different with each other. If you start like corrupting both of them, they now start like looking alike, which means that there is a noise level that you can add. And effectively, at this particular noise level, you can actually start treating these blurry samples plus noise as good samples plus noise, and reduce it back to a problem that you could like have math for. So in the easy setting where we could analyze it, it was additive Gaussian noise, we developed some very nice math and some very nice techniques. Now we have a harder problem. We have these blurry images that we don't know what happened to them. They're not really blurry. They can be something, whatever. And then we say, OK, we are going to do something crazy. We're going to corrupt them extra. But what do we win by doing this? We now convert it to a problem that we know how to deal with, in some sense. And this game, we don't have to play it ourselves, because we have to still figure out how much noise level to add. But then what we can actually do is we can train a model to do this. And how does that work? We have separated the two sets of the amazing images. These are like the photographer images. And there are all these other images that might be great and might be not. And we don't really know like if they're great or how great they are. We just know that there is a small set which we actually believe it's really, really good. And then what we do is we train this like diffusion-like classifier, where it takes as input like an image from either of these two sets. It adds noise to it. And then it's trying to predict 1 if it came from a good set, and 0 if it came from the bad set. It's essentially like playing kind of a game that we played at different noise levels. And then after we train this model, what we do is we say, OK, we start with a corrupted image. We ask our model, do you believe it's a clean image? And it says, absolutely no. 0 chance. And then we say, OK, we will increase the noise level a little bit, and then we'll ask again. And then the model says, OK, I give it like now 10% probability. This was a clean image plus noise. And then we increase more and we increase more. And then the game is, we want to find the minimum noise that we need to add, such that we confuse this classifier. And of course, there's always going to be a point, because if we add infinite noise, we are definitely going to confuse any classifier. But at this point, we kind of like also erased all the signal. So the game is we want to add the minimal amount of noise so that the signal is not erased. And then yet, we still kind of confuse this classifier. And as you saw by playing this game, you can be confused very, very easily for certain corruption types. And then you can see, like, for this particular game that we played, you can see the classifier probabilities. In the beginning, the classifier says 0 probability, and then it's like 0.35, and so on. And then there is a point where it's like completely confused. And at this point, these images are actually still used in the diffusion training. They're still used for 20% of the training updates. These like very, very noisy images, they're still useful, and we can still like run them. So how it looks like at the end is you have a data set where each data point has its own like noise level. And then you have some points that have a lot of noise, and they're only used for like a subset of the diffusion training. And there are some other points that have like less noise, and they're used for more, and some other points that are amazing and are used everywhere. So one way of thinking about the utility of data points is basically how many like denoisers can they help me learn. Amazing data points can help you learn all the denoisers. Not so good data points, they can only help you learn some denoisers. And then you go and you do this in your favorite data sets. And then the important thing is that you keep everything else fixed. So you keep the model fixed. You keep like the optimizer fixed. You keep the training hyperparameters fixed. The only thing that you are changing is how you use the data. So you're just doing an algorithmic innovation about like how you use the data. And then you see that the quality of the generated images, both qualitatively and quantitatively, improves. For example, like look at this bird. You still generate kind of the same bird. It's not that you started sampling from some other distribution. But just by doing some very like clever thing about like, not that clever actually, it's a naive thing. But just by doing something about how you use your bad data, you can actually do better than just like training on everything like everything is the same. And that holds for like data sets like ImageNet, and then you see like different examples of this. But it also works like strikingly better when you go to like much more diverse data sets that actually have heterogeneous points, like these text-to-image data sets that we train our models that generate images. So all that was for images, and that is cute. But what we really want to do is like science. And then we have actually taken this framework and we have applied it to a bunch of different applications, starting from proteins to MRI, economics, robotics, neuroscience, even underwater photography restoration. But I want to talk about my favorite application for the next 2 minutes, which is proteins. And there is a reason why I like this application. The reason is that in proteins, you can think of samples as PhD students. What do I mean by that? In proteins, you want to create a data set of how the real proteins look like the 3D structure, like these nice shapes on the left. But then the point is that to actually crystallize the protein and figure out how it works, you have to be a really good PhD student in chemistry and spend 3 or 4 or 5 years of your life doing this. And if you are very, very good, by the end of it, you have crystallized 3 or 4 proteins, okay? And we have had a lot of good PhD students over the past years, and we have been collecting this data set for the past 30 years or something. And then yet the size of the data set is much, much smaller compared to how the image data sets look like. So we have maybe 100,000 unique proteins that we know how they work, how they look in the 3D space. But if you compare this to the billions of samples that we train our text-to-image models, this is nothing. This is peanuts. But there is also another way, which is instead of actually figuring out how the protein looks like, we can ask a model, which is AlphaFold, like a synthetic model, to basically tell us, here is an amino acid sequence, how do you think it looks like? And then now suddenly, you go from a data set that was very, very small, a small data set of real proteins that PhD students made in the lab, to a gigantic data set of predictions, where a part of it, you know that you can trust it because it's coming from actual students made it in the lab. And another chunk of it, the big chunk, you actually don't know if you can trust it or no. Some model told you that this is how it is, but you're not sure. And then people say, okay, we have 2 options. We can either train on this small real set, or we can go and train on this gigantic fake set. And then they figured out that neither of these 2 options is good. Actually, what turns out to be good is you can actually start from this gigantic set and filter out whatever, according to some heuristic rule, you do not think that it's very good prediction. And they did this and they were happy for a short period of time, until they realized that this filtering essentially killed all of the long proteins. So yes, the model that you trained after doing this filtering was really, really good, but it was only good on things that were short and uninteresting, because all of the rest, they were filtered out. So if you go and after training, you kind of examine your model, how it behaves in terms of both quality and diversity, as the proteins become longer, you kind of see that the model actually is not that great on long proteins, and that is because we did filter them. It was us that we went and we removed this part from the data set. Instead, what are we going to do? Something very, very simple. So we're going to say, okay, these proteins that we don't trust very, very much, we're not going to filter them out, but we're going to be using them only for a subset of the diffusion times. And then there are some proteins that we trust a little bit more, so we're going to be using them for more of the diffusion times. And then there are the people that actually made proteins in the lab, and we're going to be using them for all the diffusion times. And now we try again, and you get to see that in this field that was kind of moving slowly for a lot of years, now we kind of have a very big impact, not because we have a better model, a bigger model. It's not an architectural innovation. We actually have a model that is 100 times smaller, but yet it beats all of these other NVIDIA models and these other really big models from these big labs because it was a data problem after all here. So I really like this application. It kind of shows that in some domains in science, it's not really about architecture, it's not really about optimizers, it's just really about data. And if we can do even naive things about how we use the data, just using them for some diffusion times and whatnot, it can still have a very big impact. Okay, so I'm gonna go to the conclusions and then finish. I have been developing this line of work of bad data in, good models out. And we have done it for different domains and different settings and different corruptions. Sometimes we know them, sometimes we don't. Sometimes we have some clean data, sometimes we don't. And I really think that this is going to be a very important direction in the future because I think we are leading towards a future where data is the main bottleneck. So far, the problem was compute in some sense because we're applying generative modeling to data-rich domains like image and text. And there the problem was not really the data, was really the compute. But now that we are moving into scientific applications, data becomes a more critical bottleneck because in scientific applications, high-quality data is really, really scarce and really, really expensive to get, and sometimes even impossible. But even in the data-rich domains, there are predictions that we are running out of data. So far, data was not a problem because we had enough data, we just needed more GPUs from NVIDIA. But there are a lot of papers right now that basically say that in the next 2 to 3 or 4 years, the models will have consumed all the data there is. So then if that happens, data is going to become a really big bottleneck for performance. We need to start considering data that we are currently discarding because we can afford to discard it, because we have more data to train on. And what I predict will happen is that for some very niche domains, like let's say math or some other medical domain, there are going to be some experts that will give you this data, but it will come with a very high cost. But then you can also get this data from not so much experts, maybe students in the field, or maybe people that sometimes they have incorrect solutions, but these are much cheaper. And then there's going to be a game of how do I give my budget among these two heterogeneous data sources? And the answer of how you split your budget really depends on your ability to extract information from the bad data. If you can really leverage this bad data by doing something algorithmic and something clever about it, then you can actually spend some of your budget there. Of course, you need some good examples, but the question is how many? Do I really need to only get good examples, or can I also learn from these cheaper data sources that have mistakes, but maybe I can have my training to account for these mistakes? And if you can actually develop these techniques, it will inform the way you do data filtering. Because right now, when we do data filtering in these big works that are part of UT as well, we kind of commit to a training objective. But now we can move past that, and we can say that maybe we will start using data, but we will be able to change the training objective based on how corrupted they are. And I think a final important thought is that so far a universal constant in all of deep learning is that when we build better datasets, we have better models. But now we are approaching this regime of we cannot make the dataset better anymore by getting more data, because we are really, really hitting a data bottleneck. But people are saying, OK, don't worry, we will actually have the models produce data. So they say synthetic data is the solution. And they kind of go and have models that are trained on a data set, produce more data, and then they keep on going. But of course, when you do this naively, there is a lot of risks. And one of the risks is this propagation of training biases and propagation of errors. And if you naively kind of train more data, more points, more models on your original points, then you have this madness effect where future models are actually starting really believing wrong things and really, really diverge. But you can apply this corruption-aware trainings and say that the synthetic data that we generated is not really real, but it's still useful if you kind of account for the fact that they have mistakes and have these processes where both datasets and models co-evolve in a good way, where it's not catastrophic. If you can do this for science, that's even more important, because now we are not really just pushing the frontier of generative AI, but we are impacting all of the models that are trained there, including classifiers, embedding models, and all of the downstream tasks. So I think denoising scientific data is going to be a next important step. And with that thought, I will finish. I'm ready for your questions. Thanks so much.
Great talk. I can't tell if that's on. So how do you expect this sort of framework to behave when you have time-varying corruption? Mm-hmm. So AI slop as an example, where you just see someone trying to do a backflip and then they fold into themselves, mm-hmm. and the expectation that that is not obviously an output that we would ever expect to be real or realistic, but
yep.
Is a situation that we run into.
Yep, that's a great question. I feel as long as you can detect how bad something is, then you can use it. So I think one way to think about it is that we want to be generating things, and then in our training set, some bad things leak. And then my kind of point of view is that if we can know that these things leak and we can know how bad they are, we can actually flag them and say, this is not my target distribution, but this is another set. It might have useful information. For example, the person doing the backflip is wrong, but maybe the background, there's a sky and there's the sun, and this particular part of the video is actually fine. So as long as we kind of know that this particular point is wrong in some way, we can be clever about how we use it, and we can leverage, we can learn something from it. But if we are agnostic to the fact that it has a corruption, then we are doomed, because I think we're going to enter this loophole of just having models produce more and more wrong stuff.